Could the next big one strike far from North America? Instead of dread Cascadia, scientists warn of a far more ominous danger brewing beneath the Indian Ocean, a complex of faults stretching under Sumatra and Java. What if our greatest earthquake threat lies hidden thousands of miles away in the Sunda subduction zone and adjacent Wharton Basin? Could this remote fault system unleash another catastrophic quake and tsunami? Seismologists say the answer is yes. A network of fractures off Sumatra has already produced a cascade of massive earthquakes, and much of it remains locked and strained. For tens of millions of Indonesians along the Indian Ocean, the next rupture could dwarf anything seen in Cascadia and might arrive any time. The Sunda megathrust fault snakes from Burma past Sumatra and Java, forming the India-Australia Sunda plate boundary. This roughly 5,000-mile-long underwater fault, roughly 5,500 kilometres, marks where the India-Australia tectonic plate dives beneath Eurasia, the Sunda plate. Here the plates grind together at about 52 millimetres per year, roughly 2 inches per year. Because the motion is strongly oblique, the velocity splits into two parts. One component pushes the ocean floor under Indonesia, thrusting on the megathrust, and the remainder is taken up by horizontal shear. The leftover shear is accommodated by faults further inland or within the plate itself, including Sumatra's Great Strike Slip faults and the mysterious conjugate fault network under the Wharton Basin. Effect the Sunda Trench, offshore Sumatra and Java, carries the perpendicular plate convergence, while strike-slip faults take up the motion parallel to the trench. The Sunda subduction zone has proved ferociously active. In the past 2 decades, it has ripped and racked itself with a procession of giant earthquakes. On December 26, 2004, a magnitude 9.1 thrust quake tore a roughly 800-mile, 1,300 kilometres segment of the megathrust off northern Sumatra. 3 months later, on March 28, 2005, a magnitude 8.6 event shattered a further 400-kilometre patch south of the 2004 rupture. In 2007, southern Sumatra saw a magnitude 8.4 quake with 2 big aftershocks, and in 2010 the region of the Mentawai Islands quaked at magnitude 7.7. Perhaps most surprisingly, in April 2012, 2 enormous intraplate quakes, magnitude 8.6 and 8.2, struck beneath the Indian Ocean, farther offshore, on what is conventionally the Indo-Australia plate, about 100 to 200 kilometres west of the Sunda Trench. In short, 7 magnitude 8 or greater shocks have rattled this chain of islands and adjacent seas in the last century or so, and dozens more in living memory. Such a run of large events confirms that many long sections of the Sunda megathrust are tightly locked and overdue for rupture. Strikingly, that 2012 West Sumatra seismic crisis was largely intraplate, within the India-Australia plate, not on the plate boundary. The magnitude 8.6 main shock and magnitude 8.2 aftershock propagated along a tangle of strike-slip faults deep beneath the sea. No one had ever recorded a magnitude 8.6 strike-slip quake within a tectonic plate. It was unprecedented. Until then, many assumed such great quakes can only occur at plate boundaries. Yet seismograms and field studies confirmed that these shocks were pure strike-slip, sliding blocks horizontally. In the absence of a major interface under stress, what happened? Researchers have found that the Indo-Australia plate's interior, under the Wharton Basin, is riddled with nearly orthogonal reactivated fracture zones. Two sets of perpendicular faults, so-called conjugate faults, crisscross the seafloor. Under the prevailing stress field, either one orientation can slip left laterally or the other right laterally. In April 2012, evidence shows both orientations ruptured in a single event, unleashing a cascade of failure. Models suggest the main shock may have ruptured multiple segments, up to half a dozen, in a region roughly 200 kilometers across. Geophysicists describe the result as a diffuse rupture plane with slip jumping back and forth between different trending faults, rather than one neat planar break. Geological detectives even found a smoking gun on the seabed, a pull-apart basin along a reactivated fracture zone. Recent marine surveys showed a shallow trough about 2 kilometers wide, 5.4 kilometers long and 70 meters deep, a classic signature of strike-slip motion. As one scientist remarked, this depression is like a stretch mark on our planet's skin, a sure sign that blocks slid apart during the quake. It sits exactly along a northwest striking fracture that likely unzipped in 2012, splitting that segment of ocean crust. In short, the Wharton quakes were powered by old faults in the ocean plate itself, unleashed by the tremendous stress of oblique subduction nearby. These intraplate faults remain under heavy strain. Indeed, prior moderate shocks, magnitude about 6.2 in 2006 and 2007, had already hinted at the danger. With the sudden demonstration of how big they can be, geologists are now scanning the Wharton Basin closely as a diffuse plate boundary where stress is still accumulating. Meanwhile, back on the continental side, the Sunda megathrust itself is still charged. The 2004 and 2005 ruptures relieved strain on their specific patches, but adjacent stretches were left locked. The patch south of the 2004 to 2005 rupture, under the Mentawai-Simeulue region, is a notorious seismic gap. Historical records and coral geology show it last broke in massive tsunami-genic events in the late 18th and early 19th centuries. In fact, scientists note that the Mentawai fault offshore Padang saw a pair of magnitude about 8.8 events in 1797 and 1833. Since then, strain has been reaccumulating without major release. Research indicates today's accumulated fault slip exceeds what those old quakes released. In other words, enough elastic energy has built up for another magnitude, about 8.8 to 9.0 failure. Indeed, the magnitude 8.4 quake of 2007 slipped only part of the Mentawai segment, leaving plenty of locked fault behind. Experts warn this overdue segment could rupture with a huge quake and generate a devastating tsunami to Sumatra's western coast. One review concludes that, unlike the northern Aceh segment, which likely will not repeat for centuries, the southern section will likely produce one or two great quakes in the next few decades. Farther south, near Java, the same convergent boundary continues unbroken for thousands of kilometers. Yet much of Java's offshore fault has not slipped in modern times, suggesting another seismic gap. Java's south coast is densely populated, over 100 million people live nearby. Recent tsunami modelling shows the stakes. Worst-case, simultaneous ruptures of two Java megathrust segments could send waves 20 metres high, about 65 feet, crashing on West Java, and 12 metres, about 40 feet, in East Java. Even less extreme scenarios still yield multi-metre waves inundating major cities. Combined with the high rate of plate convergence, these studies argue that southern Java too harbours a loaded gun, waiting to fire. In short, from the Andaman Islands all the way to Java, the Sunda megathrust is the zone of world-class seismic potential, far exceeding Cascadia in sheer scale. The geological evidence for great future quakes is thus compelling and multifaceted. Satellite GPS and coral dating have identified long, locked patches ready to break. Statistically, the recurrence intervals, hundreds of years for magnitude 9.0 on Sumatra, about 200 years for magnitude 8.8 on Mentawai, mean we may be in a period of heightened risk. And even without knowing exactly when, the process is simple. The India-Australia plate is piling on strain at centimetres per year, and friction keeps it bottled up until the fault finally lets go. When it does, the result will be a megathrust rupture, releasing centuries of built-up energy. The 2004 Quake ruptured a 1,600-kilometre stretch in minutes. The next event could easily span 1,000 kilometres of fault, slip tens of metres of crust, and shove the sea floor upward by metres, spawning a tsunami apocalyptic in scale. Aside from tsunamis, the earthquakes themselves would be immensely destructive. Megathrust events, where one plate thrusts under another, are the largest type on Earth. The 2004 Sumatra quake remains one of history's biggest. A future Sumatra-Java mega-thrust could shake much of the Indian Ocean rim. Even the strike-slip Wharton quakes of 2012 produced local tsunamis, though smaller, and hundreds of kilometres of ruptured seafloor. Buildings in Sumatra's west coast cities like Padang, or even Malaysia and Thailand, would face tremendous shaking. In short, the scientific consensus is stark. Indonesia's megathrust and related faults pose a far greater hazard than Cascadia's, thanks to faster plate motion, longer locked faults, and more recent activity. Despite this clear threat, modern early warning systems and preparedness are still catching up. The Indonesian Tsunami Early Warning System, INA-TWS, exists but needs strengthening, especially for Java's south coast, which has minimal prior events. Emergency planning must assume worst-case rupture models, multiple segments and tsunamis tens of metres high. Researchers emphasise that even if some fault patch is currently slow slipping, which could mask locked strain, evidence from tsunami deposits shows historical mega-thrust collapses did occur. Ultimately, we cannot predict the exact day, but the geologic record and physics make clear when it happens, it will be momentous. In a nutshell, the most dangerous fault today is not off the United States northwest at all, but submerged beneath the Indian Ocean. The Sunda megathrust and the labyrinthine Wharton faults have already unleashed earthquakes equivalent or larger than anything Cascadia has seen. More importantly, massive locked regions remain. These zones can and will break again under constant tectonic loading. As earthquake geologists warn, the lurking potential of this fault system is extreme, and not a matter of if, but when. Geologically literate or not, the takeaway is urgent. Billions of dollars have been spent studying Cascadia, but just as much vigilance and resources must be turned toward the Sumatra-Java boundary. Millions of lives in Southeast Asia depend on the science of plate tectonics unfolding correctly. If that fault finally ruptures, the stage is set for one of history's largest earthquakes and tsunamis. As one expert put it, think of this Indo-Australian Sunda boundary as the real seismic monster. A locked spring bristling with lethal energy, quietly counting down. Likewise, beyond the seismic and tsunami threat, the looming risks in the Sumatra-Java region include a less often considered but deeply consequential dimension: volcanic interaction. The same tectonic processes that drive the Sunda megathrust and the strike-slip faults also feed the region's immense volcanic arc. When one part of this system ruptures, it can set off a chain of responses that ripple through the crust, influencing magma movement and potentially awakening volcanoes that have long been simmering beneath the surface. A large tectonic event in this region would therefore not just be a geological rupture, but the opening act of a far broader multi-hazard crisis. Stretching along the western rim of Indonesia, the Sunda arc was born from the relentless subduction of the Indo-Australian plate beneath the Sunda plate. This collision, occurring at roughly 2 inches, about 50 millimeters per year, fuels both the world-class seismic activity of the Sunda megathrust and one of the most densely packed volcanic regions on Earth. On Sumatra alone, there are more than 130 active or potentially active volcanoes, while Java, to the east, hosts dozens more that rise above dense population centres. This alignment means that the same crustal compression building up energy offshore is also feeding molten reservoirs inland, a literal line of fire sitting behind the world's most dangerous plate boundary. Among these volcanoes, several stand out for their history and proximity to major faults. Mount Marapi in West Sumatra remains one of the most active volcanoes on the island. Its steep slopes overlook populated valleys, and its magma chambers sit within the same broad stress zone, influenced by the offshore megathrust. Even small pressure changes from a tectonic shift could disrupt the equilibrium inside the volcano, increasing the likelihood of new fissures or small eruptions. Southward, Mount Dempo dominates South Sumatra's skyline, a high stratovolcano whose recent eruption on August 21, 2023, served as a reminder that volcanic rest in this area is rarely long-lasting. To the east, across the Sunda Strait, lies Krakatau, once the site of the 1883 eruption that changed global weather patterns and generated a tsunami that killed more than 36,000 people. Its modern remnant, Anak Krakatau, continues to grow from the sea, and any tectonic jolt beneath the strait could influence its unstable cone. On Java's side, Mount Galunggung, infamous for its 1982 eruption that disrupted aviation and blanketed nearby communities in ash, represents another critical link in this chain of hazards. Each of these volcanoes sits within a few dozen miles, tens of kilometers of fault lines capable of transmitting stress from a major rupture. If a great earthquake were to strike along the Sunda megathrust, an event possibly reaching magnitude 8.8 or 9.0, the redistribution of stress throughout the crust could have immediate and delayed volcanic effects. Pressure changes deep underground might cause magma to rise or shift, opening new vents or triggering flank instability. Ground shaking alone, lasting for several minutes, could damage volcanic monitoring stations, gas sensors, and deformation networks, blinding scientists at the very moment when volcanoes are most likely to react. Coastal volcanoes would face additional threats from tsunamis generated by the quake itself. These massive waves, which can travel at more than 500 miles per hour, about 800 kilometers per hour, could strike the base of volcanic edifices, saturating their lower slopes and potentially causing landslides or flank collapses. When the slope of a volcano gives way, especially one with a hydrothermally weakened core, it can trigger a secondary eruption, as seen in historical cases where sudden decompression of magma chambers produced explosive results. In such a chain of events, the hazards would not unfold in isolation but overlap, amplifying each other. Earthquake-weakened infrastructure could crumble under the additional load of volcanic ash. Roofs already cracked by shaking might collapse under ashfall only a few centimetres, an inch or two, thick. Flooded coastal zones could turn into mud-filled traps if lahars, volcanic mudflows, begin to pour down the slopes of nearby volcanoes. Ash clouds could ground relief flights, while tsunamis would destroy roads needed for evacuation. In the chaos following a megathrust rupture, even a moderate eruption could multiply the death toll and complicate every phase of response. The Sunda megathrust is particularly concerning because of its velocity and the degree to which it remains locked. Much of the fault is accumulating stress that has not been released since the catastrophic 2004 Indian Ocean earthquake, farther north near Aceh. Seismologists have warned that the southern segment, off the coast of West Java and southern Sumatra, is nearing its own breaking point. The volcanic arc behind it runs almost parallel to this fault line, meaning that the distance between rupture and magma chamber is sometimes less than 60 miles, about 100 kilometres. Few regions on Earth combine such proximity of tectonic and volcanic danger with such high population density. Java alone is home to more than 150 million people, many living within sight of active volcanoes. A plausible scenario would involve a major rupture in the Sunda megathrust off the southern coast of Java. Within minutes, a tsunami races toward the shore, inundating fishing villages and coastal cities. Inland, the tremor destabilizes slopes around Galunggung, cracking its flanks and allowing rain and groundwater to penetrate new fissures. In the days that follow, steam vents increase, tremors grow shallow, and magma pressure builds, leading to a fresh eruption while rescue efforts are still underway. On Sumatra, a similar sequence could unfold. A great quake near the Mentawai Islands sends strong shaking through the highlands, where Merapi and Dempo respond with renewed seismicity or eruptions. Communities already devastated by the quake and tsunami find themselves facing ashfall and lahars flowing down saturated river valleys. If Anak Krakatau were involved, the scenario could worsen, as a collapse of its unstable cone might generate a secondary tsunami across the Sunda Strait, striking both Java and Sumatra again. The implications for preparedness are profound. Emergency planning cannot treat earthquakes, tsunamis, and volcanic eruptions as separate categories. Each is linked by the same geodynamic system, and the failure to account for cascading hazards leaves millions vulnerable. Monitoring networks need redundancy, backup power, multiple data routes, and satellite communication so that a quake does not blind the volcano observatories. Evacuation routes must consider dual threats. People fleeing tsunami zones might encounter lahars or ashfall farther inland. Public education must emphasize that an earthquake could be the prelude, not the conclusion, of a disaster sequence. Ultimately, the Sunda megathrust and its neighbouring faults form more than just a seismic hazard zone. They are the beating heart of a vast tectonic-volcanic engine whose effects can reverberate across oceans and skies. A rupture here would not merely shake the ground, but awaken a corridor of volcanoes that trace the subduction zone from the Andaman Sea to eastern Java. The cascading effect, earthquake, tsunami, eruption, would likely surpass even the devastation of 2004. Not because of magnitude alone, but because of compounding impact. For a region so densely populated and geologically alive, preparation means more than building for the big one. It means understanding that in this part of the world, when the Earth moves, the mountains may answer. If you found this breakdown insightful, do not forget to like, share and subscribe for more deep dive coverage on real-world tectonic and volcanic phenomena. Every click helps us keep creating high-quality, science-driven content. And hey, tap that hype icon to help this video reach an even wider audience and keep the conversation going. Your support really makes a difference.